Hello, and welcome to our webinar today to discuss best practices in fibre optic dissolution testing. My name is Claire England, and I'll be your moderator for today. Before we begin, I'd like to take a moment to cover some logistics. At the end of the webinar, we will hold a short question and answer session. To ask a question, click the Q&A button at the bottom of the screen, type your question, and hit send to send to the host. In today's webinar, you'll hear from Dave Kowalski. Dave has been involved in the commercial side of life science companies for nearly 20 years, with the majority of his time spent in dissolution-related applications. Dave has held numerous sales management, and product management roles throughout his career, and he is currently serving as a technical consultant to Pion, helping to support their fibre optic product portfolio. We thank you for attending today's webinar, and without further ado, I'd like to introduce you to Dave.
Thanks for the kind introduction. Hello, everyone. My name is Dave Kowalski, and I'm excited to be talking with you today about in-situ fiber optic dissolution systems and some best practices, which have come about through my nearly 20 years of experience with the technology. I've been fortunate enough to have worked with many of the innovators in the field, and I hope to be able to help you in either your journey to better utilization of your current system or your decision as to whether this technology is a fit for your testing environment. Just to make sure we're on the same page, we have allocated 45 minutes for this webinar today, the first 20 to 25 minutes of which will be the presentation. Over this time, we'll be covering some basics of the technology and why it is used so broadly across the industry. I will then get into some specifics as to how to get the most out of the technology, where it can be applied, and how to think about the types of experiments you can run on the system. The remaining time will be set aside for your questions. Today, you will find microDISS systems throughout development labs in pharma, CROs, CDMOs, and academia. However, when I started with Pion nearly 10 years ago, the microDISS was in the very early stages of adoption. A microDISS is the system name for a rainbow fiber optic detector, a mini-bath small volume dissolution bath, and AU Pro software. While the rainbow has roots in a QC dissolution environment, the microDISS system was co-developed with Sudhakar Gerard's pre-formulation group at Novartis in 2005. The group needed a tool which could measure intrinsic dissolution earlier in the development process, where there was not enough material for traditional Woods apparatus experiments. The ability to run experiments with small amounts of drug substance continues to be a primary driver for adoption of the technology today. But it is the versatility of the platform which has made it so prolific across the industry. The system is frequently used for salt screening, precipitation studies, biorelevant dissolution, amorphous solubility, first-order infusion studies, formulation vehicle screening, supersaturation experiments, media transition assays, and of course, where it all started, mini-intrinsic dissolution. I'm sure there are more, but this gives you a pretty good indication of the flexibility. Scaling everything down has an impact not only in the amount of data you can acquire earlier, but also the cost of that data. Combine all this with the fact that you're getting data in real time, and you have dramatically improved the speed at which your decisions can be made at every stage of development. You are no longer waiting days or more for the results of a dissolution study in order to make critical program decisions. The data is there on screen from the onset for you to view, interpret, and act. The robustness of the system is also incredible. It's just plain hard to kill a rainbow. The system works day in and day out. In order to have a system to meet the demands of the dissolution environment, you need to start with the right detector. Keeping in mind that dissolution is by definition a kinetic study, there can be no assumption of a steady state during the assay. Accurate analysis requires the simultaneous acquisition of the entire UV region in order to characterize the chromophore as well as the baseline. While in development in the mid-1990s, the decision was made that the system should use individual diode array detectors for each fiber optic channel. This is still the case today and is a critical feature of the system, which allows Pion to have all the advantages previously discussed. If we assume a steady state in dissolution, our attempts at finding appropriate calculation settings will fail in turbid environments. We need a detector which can simultaneously collect from multiple channels and collect the full UV region at every acquisition. While it is important to understand the history and context of this technology, the reason many of you are attending this webinar is to pick up on or refresh some best practices. This is especially important when we start to discuss the proper use of functions like second derivative analysis. Detecting in a turbulent environment, like would be the case with many of the applications discussed, without physical filtration requires the use of math. Basic baseline correction techniques like line or point work well for filtered samples or samples with scattering from large particles. But when scattering is caused by small particles, Tyndall and Rayleigh scattering dictates the baseline. Second derivative does a better job at removing the effects of this scattering and allowing for accurate quantitation of the analyte of interest. While second derivative spectral interpretation is powerful, it must be applied properly in order to not report on artifact data. Let's first discuss how to use both direct spectra and second derivative to assess the overall quality of our data file. The key questions I must answer to have confidence in the data file are, number 1, do I have a good blank? Number 2, is my standard curve linear? Number 3, am I within the linear range of the detector? Number 4, are my sample spectra well behaved? Number 5, does my standard and sample spectra match? In order to answer these questions, I'll use a variety of software tools in both direct spectra and second derivative. If I were asked to interpret a data file, here is the process I would follow. I have looked at thousands of fiber optic data files in my career, and I can tell you the number one source of bad data is a bad blank. A bad blank can carry through all spectra and allow us to start an analysis when the system is not functioning optimally. The blank, or 100% T as it is called in the Pion software, tells us about the overall quality of the light path, which includes the lamp, shutter, fibers, lens, mirrored tips, and spectrophotometers. If the lamp is beyond its recommended hours, the blank will tell us. If the probes, lenses, or mirrors are dirty, the blank will tell us. If there is damage or breakage in one of our channels, the blank will tell us. Analytically, the blank tells us where there is enough light to analyze. But the collection of the 100% T alone may cause us to miss some of the above. We must make it our standard operating procedure to use 100% T in diagnostic mode in conjunction. Diagnostic mode is accessed by a toggle of the folder icon in older versions of AU Pro and by the camera icon in AU Pro version 7. It is a wavelength versus absorbance display of our blank media compared to our 100% T. Put simply, it is comparing the blank to itself and displaying the data as spectra rather than light intensity. If the blank is changing, as would be the case with a dirty probe, the diagnostic mode scan would show it. If I have a good blank, the spectral display should be at the baseline, plus or minus a few 1,000ths of an absorbance unit. For more on the use on diagnostic mode, please refer to the manual or contact Pion tech support. Some best practices to consider when working with 100% T in diagnostic mode are listed on this slide. Each of them enable the collection of a good blank and test the collected 100% T in diagnostic mode. Please keep in mind that diagnostic mode scans are not saved, so it is recommended that you collect the blank media as a standard with concentration equal to 0, which will save the blank absorbance spectra in the file for investigations or confirmations at a later time. The rainbow is a relative absorbance instrument, which means that a blank and standard need to be acquired for each channel with which you intend to collect samples. The software needs at least one standard spectra to be collected in order to calculate quantitative sample data. You can collect as many standards as you want, and beyond one point, AU Pro will calculate a standard curve, which will give you more information about your API, as well as give you more confidence in the quality of your data. It is always preferred to prepare your standards in the same media as your dissolution test for potential differences in refractive index and/or molar absorptivity. This might not be possible due to solubility reasons, so I will go into some of these considerations on a future slide. Once I have my first standard acquired, I cut down the view window settings to be my absorbing portion of the spectra plus 40 to 60 nanometers so that I can see a representative portion of the baseline. As I'm acquiring the next standard, I go to Tools, Show All Spectra, in order to overlay the standards which I am collecting. I make a qualitative assessment of the data in direct spectra to make sure the next collection makes sense. If I double the concentration and the absorbance does not double, then something probably went wrong. I might have a bubble preventing the tip from filling, my tip might be loose, or I did a bad job in sample prep. In either case, I would do some investigation before proceeding. Also, once I have collected 3 to 4 standards, I start looking at my calibration curve at each collection to ensure I have linearity and an R-squared value greater than 3 nines. It is also at this point where I assess my path length choice. For example, if I am expecting the concentration of my final test solution to be 100 micrograms per mil, then 10 micrograms per mil is 10% of that. If when using a 5 millimeter path length tip, the absorbance in my calculation region is 0.2 absorbance units, then I run the risk of oversaturating the detector in the full concentration solution. If I change to a 2 millimeter tip, the expected absorbance of my 10% solution is around 0.08 absorbance units, and my 100 microgram per mil solution around 0.8 absorbance units. It is preferred where possible to have the absorbance of my final concentration solution be between 0.5 absorbance units and 1 absorbance unit. This is below the upper limit of the instrument, but keep in mind scattering further decreases transmittance, thus increasing absorbance. In highly turbid environments, you may also consider reducing the path length to get the absorbance below 0.5 absorbance units. Keep in mind that we will work as far out in the absorbing region as possible using second derivative, but we will discuss that in more detail shortly. For now, I use direct spectra and a shoulder or peak max to assess spectral quality. Let's now consider the case that the solubility of my crystalline API is significantly different than my formulated substance. How do I create a standard curve which is representative of the assay and adequately covers the entire concentration range? This is a very common situation with the number of solubility enhanced products in development. While there is no one magic bullet, there are a couple choices. Choice one would be to choose a co-solvent system with as small a difference from the dissolution media as possible. If you can use a 90-10 disso media to co-solvent ratio, this will result in a media system which in most cases is still comparable to your disso media alone. Avoid using 100% co-solvent wherever possible. The benefit of this approach is that the curve can encompass the concentration range of your sample. The risk is that your standard and sample spectra might not have a comparable region which can be used for calculation. Remember, this is a relative absorbance instrument. Choice two is that you prepare a curve in 100% dissolution media where you have solubility and assume linearity holds out to where your formulated sample solubilizes. The benefit of this approach is that your sample and standard spectra will match, even for only a small concentration range. The risk is that you are assuming the linearity of your standard curve holds from the limited region where you have prepared the curve out to where your max concentration is. Consider the goal of the experiment when thinking through these two choices. Both have potential of introducing error, but is it an error you can tolerate? When working with in-situ UV data, saturation of the detector, absorbance above 1.8 absorbance units, is going to happen. First, let's make sure we're on the same page as to what saturated spectra are. Given the inverse relationship between absorbance and transmittance, absorbance equals the negative log of transmittance, a saturated absorbance spectra is the absence of light. There is a practical limit at which the system cannot operate. If you have run the system long enough, I'm sure you have seen a flat-lined, maxed-out spectra where the turbidity blocked all of the light. In this case, perhaps a revised design of experiments is needed. But assuming you still have spectra, which in some region look representative of your API, the question becomes, can you still work with the data? The answer depends on whether your data meets the spectral quality criteria covered on the next few slides. The next step in my data interpretation troubleshooting process is looking at the quality of my collected sample data. As previously discussed, I need to evaluate the extent to which my sample data is saturated. Make sure when evaluating sample data for saturation that you're using direct spectra analysis and you're not applying a baseline correction. To do this, I am again using the Show All Spectra function found in the Tools dropdown. Once I am satisfied that I am either not saturated or that I have some features of my spectra which offer the potential for calculation, I then convert my data to second derivative using the second derivative checkbox in the calculation settings window. I would select a 10 to 20 nanometer range of the second derivative, which could be a peak or half a peak depending on broadness. I want to work as far out in the UV region as possible where I have adequate signal. I would then confirm my standard curve is still linear with these new calculation settings. Assuming it is, I am then ready to assess the quality of my sample spectra data and compare the spectra of my samples and standards. In the Show All Spectra view under the Sample tab, I look to make sure all of my spectra are passing through a precise point of intercept on the x-axis in the area of my calculation setting. One of the properties of second derivative analysis is that regardless of concentration for a given species, all data will pass through a precise point of x-axis intercept. This tells me a lot about the quality of my data, and it is this property which allows Pion software to calculate concentrations of a multi-component API system using zero intercept points, a method Pion calls ZIM. Shifting of the x-intercept points indicate either an issue with my data or a speciation event in situ. This causes me to question the relative quality of my data and may cause me to choose a different calculation region, look at my data as qualitative rather than quantitative, and or go back and revise my experiment design. Once I have confirmed that my samples are well behaved, I must then confirm that my samples and standards have the same spectral features. AUPro software offers a convenient way to overlap sample and standard spectra. Within any channel box in the Dissolution tab, you can right-click and select Coordinates in Spectra. This feature will allow you to trace the concentration curve with the mouse, and a window will display the overlay of standards in blue and samples in pink. Assuming your spectra are well behaved and the standard and sample have the same shaped spectra, you will see perfect overlap and consistent intercept points for the duration of your experiment. Confirming that they have the same zero intercept points within the calculation setting window is a great way to make this comparison. Keep in mind, you can change the display range of the overlay window by adjusting the view settings and choosing a more narrow wavelength region. If you did have a speciation event or you saturated your detector, then you would be able to identify the point in time when that happened, which can be very useful qualitative information. When implementing a dissolution assay early in the pre-formulation process, you are going to have to think through your design of experiment in order to get the most utility out of any in situ system. I am a big fan of the mantra, start with the end in mind. If your target dose is 1 milligram per mil, if your solubility is less than 10 micrograms per mil, you're going to have a ton of excess solid in your test vessel. Think about what you are really trying to accomplish and consider alternative experiment designs. If all you need is rank ordering, you can probably live with some noisy data. If your goal is trying to determine the absorption potential of a formulation, consider using FLUX as an indirect measure of solubility and dissolution rate. If screening discovery compounds and you don't have a standard, simply collect blank media as the standard, and then bin your compounds by area under the absorbance curve in Excel. There are hundreds of different experiment designs, which will lead you to the ultimate goal of identifying an ideal candidate or formulation. It may take a couple tries to get the parameters right, but start with the best thinking and adjust accordingly based on what the data tells you. That is the true advantage of this technology as I've seen it. You have a ton of data to work with. Let it guide you and you will get amazing value from in situ dissolution testing. Using a microDISS system can allow for data collection, which has previously been very difficult, if not impossible. The density of data you can collect in real time using a very small amount of material is unparalleled. Taking the time to think through what we covered today and implement these best practices will ensure greater success with the instrument. This presentation is full of tips and best practices which you can start implementing today. If you are new in your fiber optic dissolution journey or considering your first system, I hope this presentation gives you a taste of the ways in which Pion technology can significantly impact your dissolution testing environment. Thank you for your time today. Why don't we get started with some of those questions?
Okay, Dave, the first question that we have in is what are some approaches for improving the performance of the probes in highly turbid environments?
Thanks, Claire. Obviously, a lot of the assays we talked about today, involve high levels of turbidity that we're still trying to calculate and analyze in the presence of. Some of the things that our customers have used successfully is, off-centering the probe. So instead of putting the probe directly in the center of the microDISS vessel, to put it closer to one of the walls. That can be done by adjusting the Allen screws on the top of the mini bath and sliding the probe manifold to one side or the other. Keep in mind that if you're doing both the typical volume, the 25 millimeter, which is the 20 mil vessel, as well as the small volume vessel, the little test tubes, that off-centering on the large vessel will mean you're probably going to miss the test tube. So keep those things in mind. Some customers have tried using screens over the years to prevent particles from going in there. For some applications, those work great. For some of them, the analogy is a screen door in a snowstorm, and no liquid gets through the tip, which obviously defeats the goal of the experiment. So these are a couple of the things. Start first by off-centering it, and then work with Pion applications and tech support on your specific application challenges, and we might be able to figure out some ways in which we can help.
Perfect. Thank you very much. Second question is, can you use the same probes in both a microDISS and a traditional dissolution apparatus?
So the short answer is yes. And it actually is done very commonly in the industry. So oftentimes you'll find a rainbow sitting between a traditional, USP or EP version dissolution bath. Pion has a suite of accessories and consumables to allow for integration. Obviously, with some of the older dissolution baths, the VK7000 being a quite prolific one, there's a range of vessel covers and adaption options that exist. So again, you talk with your Pion sales channel about what baths you use, and we can guide you in terms of what accessories are available, or if we don't have them, where you might be able to source those types of accessories. But yes, the rainbow can be used in a traditional dissolution bath, and it is very commonly done so because you're typically working with a range of different drug substances and drug products.
Brilliant. Thank you very much. Another question is concerning calibration curve. Is it necessary to do several calibrations if we change medium during dissolution? For example, a two-step dissolution, additional intestinal medium on gastric medium.
Yeah, so Pion's done this work for quite a while. Some of this preliminary work was done and published out of Neil Mathias's group at Bristol Myers Squibb. So even as early back as I think 2012, 2013, you'll find publications that speak to the two-stage dissolution experiment. I think he was looking at proton pump sort of risk assessment with some of the cancer drugs they were working on. But yes, so there's a couple ways in which we can do this. The way I typically advise customers to do this is in your standard 1 tab, collect all of your acid phase standards. In your standard 2 tab, collect all of your basic phase, intestinal phase standards. And then you would basically show both components. So the system would theoretically be thinking of this as a 2-component system. But really what you're doing is you're looking at the release of in the acid phase as compared to the acid standards. And then when you do your transition at 30 or 45 minutes, you then sort of make the switch. In order to get a nice clean report, you'll probably have to export this and cut and paste in Excel, but you'll be able to visualize it within the software as the experiment's going on by taking this approach. There's a few more tips and tricks that go along with that in terms of collecting blanks and applying the right 100% T to each. So your original 100% T would be in gastric. And then what you would do is save the file and export the gastric phase. And at the end of the experiment, you would take the probes, clean them, and put them into the combined media system, which is representative of the intestinal, and blank again and save that file as your basic. Consult with us on how best to do that. And depending on what you're trying to accomplish, we can devise a better protocol. But those are some of the tips that go along with running a 2-step disso.
Yes, thank you very much, Dave. Another question is there any step-by-step guides available for data calculations and troubleshooting?
Yeah, so great question. I guess most of the time I follow the process as described in this presentation, starting with the blank and then working through the standards and the samples. As it pertains to a written out protocol for data interpretation, I know it does not exist today, but it is something that we can take out of this webinar as an action that we can combine. In addition, the attendees would probably be interested to know that Pion is working on a training video library. A lot of those videos are in post-production right now, and we're hoping to have those out for everyone to view by the end of June.
Perfect. Another question is, do you offer a fiber optic system for USP dissolution apparatus 1 and 2 as well?
So yes, this kind of pertains to the previous question about, can you use the same probes in both the microDISS and a USP bath? That answer being yes. If this question is targeted more for a GMP environment, then Pion has a software platform called Disso Pro, which is full 21 CFR Part 11 compliant and has all the associated documentation. And the use of Pion probes in GMP QC Disso has precedent. Data has been reviewed and approved by the FDA, though nothing exists in the form of a public manuscript. The people who have used this technology have typically used it as an alternate analytical approach to the HPLC data they filed with the drug. But yes, the answer is yes. In almost every case, I can't think of a single major USP 1-2 dissolution manufacturer where these probes couldn't be used.
Thank you. Another question is, can you use fiber optics in a regulated dissolution environment? Does the FDA USP approve this?
Yeah, so I think I partially answered that question in the last one. So the big thing is, does the FDA approve it? The FDA doesn't approve technology. They approve drugs. And, we know based upon the clients we work with and actually the history of this technology coming out of QC Disso, that yes, fiber optic technology has been used as a release test for final QC Disso. You will find it in Chapter 1092 of the USP as an alternate analytical approach. And it basically, like everything else the USP talks about, it needs to be validated against the benchmark, which for dissolution is manual sampling. So any level of automation you apply to your dissolution bath has to be validated in that way. And fiber optics fits that mold as well.
Okay. Is it possible to go into a bit more detail on the differences in baseline connection and when you use each?
Yeah, so the manual does a pretty good job of that. Talking about, I'll be honest, when it comes to actually, filing or reporting on data, I always end up in second derivative. But I use the different baseline correction techniques that the software offers depending on the type of sample I'm analyzing. So in its most simple form, I use a pointer, a line to remove any large scattering events that are occurring on the baseline. But ultimately, I migrate to second derivative because second derivative just does a much better job characterizing a baseline, which is more representative of the Rayleigh or Tyndall scattering that we see with the small particles. To go into each, I don't want to take that time now. I'd be happy to do that, on a one-on-one at a later date. But yeah, Pion offers a range of different baseline correction techniques, and each of them have their place. But I would say for 95% of the files that I end up helping clients with, we look at direct Spectra for the reasons mentioned in this webinar. And then ultimately we figure out the best second derivative range to use to get reliable, trustworthy data.
Thank you. What is your preferred method for getting rid of air bubbles stuck in the probe tips, particularly on the 2mm or 1mm probes?
Yeah, so the smaller path length probes do present a wetting problem. So breaking that air liquid surface tension can be quite difficult if the probes are just resident in the vial. So our best practice for using those smaller path length tips is actually to pre-fill the tips with the media that we're going to use. Just a drop or two will do the trick. Because once they're wetted, they'll wet very easily within the vial. But putting them in dry into a dissolution test vessel, it can be difficult to break that surface tension and actually fill the tips with liquid. So that would be my suggested best practice in terms of the smaller path length tips. In all cases, wetting wouldn't hurt, but the 5 and the 10 and the 20 millimeters that the system can use wet relatively easily because of the volume to surface ratio. Whereas the small ones, they can be quite difficult to wet. So pre-wetting them, just taking a pipette, squeezing some liquid through the tip and getting a few drops in there can make all the difference.
Brilliant, thank you very much. Does it work for triple combination oral product for drug release percentage?
I'm sorry, Claire, can you repeat that one? I missed a part of that.
That's okay. It says, does it work for triple combination oral product or for drug release percentage?
So yes, originally Pion only had Zim as a tool to calculate multiple components in a solution. And I saw another question. I'll answer it in line with this one, just because it fits. In second derivative, you will always cross the x-axis. It's impossible not to for a spectra. So you'll always have 0 points of intercept when you apply the second derivative to an absorbance spectra. So that being said, the ZIM points, trying to characterize more than two components, it's very difficult to find unique points of intercept to a single analyte when you have 3 or 4 or 5 analytes present. The practicality of that goes way down. So ZIM is really intended for a 2-analyte system. For a 3 and 4 analyte system, Pion has integrated in their advanced software the ability to use linear regression analysis. And so, yes, in many cases, I think we have a white paper coming out very soon, actually, which talks about these triple combination products and how to use in-situ detection to characterize the real-time release of those.
Thank you. Is it possible to use microDISS with molecules not having chromophores? And also why the tip length needs to be chosen according to the sample concentration?
Okay, 2 very different questions. This mini bath unto itself can be used for any small volume dissolution experiment. You would just have to take on the detection onto yourself for molecules without a chromophore. The fiber optic system is a UV-based detection platform, and so you need a chromophore in order to analyze. But you could absolutely use the mini bath as a small volume dissolution system and collect fractions manually and analyze those by some other means. As it pertains to why the tip length needs to be chosen according to sample concentration, it ties back to Beer's law. So with path length being a critical variable within Beer's law, we need to optimize that path length according to the solution we intend to analyze. Offline, we have the ability to concentrate and dilute. In situ, we don't have that ability. So we need to make sure that the tip we choose will allow for the collection of data, the detection of the analyte in the concentration range necessary so that the absorbance fits within the operating range of the detector. So if we have a 20 millimeter tip on our probes and we're analyzing a very high concentration solution, then the amount of molecules in that tip will be too great and the light will all get absorbed by those molecules and we don't get any light back to our detector, so we can't actually process anything. Vice versa, if we use a 2 millimeter tip and our concentration is too low, then we won't have enough molecules to analyze and we'll be operating much too close to the baseline.
Okay, great. Is it possible to get data processing software on individual scientists' computers without having to buy full new licenses?
So Pion offers offline licenses. This is more of a sales question where I'm not as, even though I support sales, that's more of an operational sales question. So, I do know that Pion sells packets of offline licenses. So if you have multiple users who need to access to the software offline, then you can talk with Pion sales about how to get those offline license packets according to the number of users you need.
Great. Another question in, could you talk about excipients, please, about dirty media?
So obviously, excipients can introduce a couple different variables to the test. They could absorb, in which case then you have a conflicting absorbance with your analyte of interest, and you'll probably have to do some level of ZIM analysis or linear regression to simultaneously measure the excipient and the analyte of interest. It's possible you're going to be able to get rid of most of that interference. If we're thinking about polymers, they're going to absorb early. Whereas if our chromophore has some sort of fingerprint out 350, 400, we'll be able to use that region without much interference from the polymer. Dirty media, I assume you mean like FESIF type media. Obviously FESIF media can impact the transmittance of the light through, without any analyte present. So it's something we have to use our 100% T to look at. A lot of the FESIF medias over time will cut off all light below, 290 or 300. So if we have a chromophore that doesn't have any features out beyond that point, then analysis in FESIF is probably going to be quite difficult. So we just have to consider, are my excipients going to absorb and interfere, in which case I have to take analytical approaches? Are they only going to scatter, in which case I can take baseline correction approaches? But at some point I need to get light. So if my media is absorbing all my light, whether the molecules within the media or the turbidity within the media is scattering it all away, then, I'm not going to have a very effective test. And that's where thinking about how to design your experiment comes in, paramount. Even though you want the data in FESIF, if your chromophore is done by 240 or 260, unfortunately, you're probably in some other form of analysis to get the data you want. So thinking through the practical limitations of the technology and how to apply it will give you the best chance of getting the most out of it.
Brilliant, thank you. I think we have time for another couple of questions. So another one in, Dave. If a blank channel is applied during a two-stage dissolution experiment, would taking T100% in the beginning of the experiment, and then in brackets FASSGF, and 100% after the end of the experiment, be still recommended?
So the blank channel can be a convenient way to assess these differences as it pertains to transmittance. But keep in mind that all of these channels transmit slightly differently. So by applying the blank channel from gastric to intestinal, you'll get a relative quantitative number. You'll get a pretty good qualitative assessment of what's happening. But if you really want the exact quantitative number at the end of the experiment, it is still recommended that you collect the blank at the end. So you can choose both approaches. The blank and reference channel are check boxes that can be turned on and turned off. But for the most accurate quantitative data, I would still recommend collecting the blank at the end of the experiment, taking extra care to make sure the probes are clear and free of anything that could carry over.
Brilliant, thank you. And lastly, is this equipment compatible with all USP dissolution apparatus?
So the answer is no. Apparatus 1 and 2, absolutely. We've covered that already. So you're not going to have any issue with any of the major manufacturers. Pion has, we've integrated into enough of the USP 1 and 2 bats out there that we know how to get that done. USP 3, I've never seen that successfully done, and I can't even think of a practical way to do that given how an apparatus 3 works. Apparatus 4, yes, that we have clients doing that on a regular basis. Depending on whether you're open loop or closed loop, would require some slightly different plumbing. Closed loop is easy. You just put the probe in the bottle and you're looking at the accumulation of analyte in solution over time. Open loop's a little more difficult because you would need to create some sort of vessel to collect the fraction as it comes out of the flow cell and analyze that before it goes to waste. Let's see, 5 and 6 are modifications of 1 and 2, so those are pretty straightforward. And 7, no way. 7 is like 3. There's no way that we can introduce fiber optics, Pion fiber optics to that today. I can't even, again, think of how you could feasibly do that and get what you needed to get.
Okay, great. Well, I think, Dave, that brings us to the end of our presentation today. I just wanted to say thank you to everyone who's attended. I hope you've found the webinar interesting. There was one last question somebody raised about whether the presentation will be available afterwards. And the answer to that one is yes, we will be circulating the presentation around to all attendees in the next few days. So please look out for that in your emails. But thank you ever so much, everyone, for attending, and I hope you have a great rest of your day.
Thank you, everyone.